Hey everyone, welcome back. This physics lesson is all about looking at the motion of objects that are fitting in a certain criteria. That criteria is known as constant acceleration. Objects that are constantly accelerating or maybe constantly decelerating. And we look at this in particular because there's actually a lot of real life scenarios that match this or very closely match it, and therefore we can do a lot of practice physics calculations, physics problem solving using this scenario. Also, in this scenario, there are some physics equations that show up that you can use, that you can apply to describe objects that have a constant acceleration. So that's what we're going to be working on today. Now, first, before we get into that directly, we have to remember vectors. I talked about vectors more in a prior video. So if you're like, what the heck is a vector? Stop right now and go back and watch one of those earlier videos. Okay, hopefully you remember that certain things like displacement, velocity, acceleration are vectors. That just means the direction is taken into account. Now, that's all well and good, except we're about to do some physics calculations. You could say that something has a velocity of 5 meters per second to the north or to the right, but you can't plug that direction into a calculator easily. At least, I can't take out my TI-89 and plug in 5 meters per second and then type out north, south, right. All right. Instead, we're going to use a convention, because the great thing about vectors, this direction can be represented mathematically using positive and negative signs. What I mean by that is, if something is going to the right, again, I can't write right in my calculator, but I could use, say, positive numbers to represent things moving to the right. The positive just means towards the right. And therefore, if there's ever something in the same math problem, the same physics problem that's going to the left, while I can't write left into my calculator, I could use the opposite sign, negative. And your calculator can keep track, of course, of positive and negatives. That's how we will come up with, and that's how we'll utilize direction. And if your calculator spits out a negative number, that means that value is in the leftward direction. If it spits out a positive, it's to the right. Similarly, usually by convention, up is given as positive and down is given as negative. To be honest, you can choose whether you want right to be positive or negative, but by convention, right is positive, up is positive. If you do something different, you might want to label that on your paper just so your teacher or your professor, whoever, doesn't get confused. Okay? So that is how we're going to utilize vectors when we're doing these math problems, because that's what we're getting into. For certain objects, there are scenarios where they have a constant acceleration. And what that means is what I have written right here. This is kind of what constant acceleration means in a math sense. It means whatever acceleration you're starting with is what you have at the end, and of course is what the average is. If I have the same string of numbers, 3, 3, 3, 3, 3, 3, you start with 3, you end at 3, the average is 3. The acceleration is staying the same. We learned an equation for average acceleration. Average acceleration. It looked like this. Delta V over delta T. That's equal to V minus V naught divided by T minus T naught. Remember, normally we would say T naught is just 0. We'll start the timer with however we began the problem. So you're left with this. V minus V naught divided by the amount of time. Well, the average acceleration is the acceleration. So I have A equals V minus V naught divided by T. I could multiply both sides by T and get AT equals V minus V naught. I could add V naught to both sides and get V equals V naught plus AT. And look what I just did. This is this equation number 1. When you have constant acceleration, there are 3 physics equations that you can use. I just showed you where number 1 came from. I'm not going to show you where 2 or 3 came from. Okay? It is helpful sometimes, and we'll do it in these videos, sometimes seeing where certain physics equations are derived from. It can be valuable, it can be insightful. These last 2, not really in my opinion. You could Google it if you're really interested. But these 3 equations can be used. Mr. Thrasher, I will give them to you in my class. They're on the AP Physics 1 equation sheet. These are equations that you can use when an object has a constant acceleration. Now, the key idea is what I have in red right here. You can only use these if the acceleration is constant. Some problems you might encounter might start off with some acceleration and then 0 acceleration, then a different acceleration. You can't use these equations for that whole scenario. You can only use them when the acceleration is constant, whether it's positive, negative, or 0. Okay. Also, we have this delta x. Remember, technically delta x is x minus x naught. Well, usually we say x naught is equal to 0. So a lot of times in this equation right here, this x naught, we'll just be plugging in the number 0. Okay, that's what most conventional textbooks use, physics professors use, teachers use, etc. Okay? Now, I've gone over that. The last part on here isn't any more notes. I'm done with notes. I do, however, have an example problem. Here is us practicing a scenario all about constant acceleration. I tell you that in the problem. I recommend you read this problem over, hit pause on the YouTube video, and try this out. Can you do this calculation? And then hit resume, and then if you want, you could watch me go over the solution. Okay? Go ahead, hit pause, try it on your own. I hope you really tried it because it's good practice. But if you were stuck, or if you're just checking your work, or if you were just lost completely, whether you got a little ways, no ways, let's go over it. The first thing, and this is really kind of the first example that we're going to get good at reading tougher physics problems. And what you got to first get good at is pulling out information. There's a lot of information in this question, in this classical kind of physical problem. Okay? First, you got to know what you're trying to solve for. What are you trying to calculate in this problem? Here it's pretty easy because it lays it out in the last sentence. It's asking you to calculate the time. The time it took Mr. Thrasher to start at rest, go 4 meters, and reach a velocity of 5 meters per second. So I'm looking for time. So of course I want to calculate the time. Now I'm given other pieces of information. What information am I given? Well, it says that I start at rest. This one's maybe actually a little tricky because it's not obvious, it's not explicit, but I'm told the initial velocity. The initial velocity of this bike rider, Mr. Thrasher, is 0 meters per second. It says that the person uniformly accelerates to 4 meters. Is that an acceleration? No, it says they uniformly accelerate for 4 meters. That's their displacement. They accelerated for 4 meters. And then they reached, after those 4 meters, a final velocity of 5 meters per second. So you got to get good at pulling out information. Okay? Now that I've done that, what equation should I use to calculate? And this is what students always ask. Mr. Thrasher, how do I know what equation to use? And to be honest, that's the ball game. If you always knew what equation to use, this class would be a piece of cake. The struggle is in trying to and developing the skill to try certain equations. Does it work? Does it not work? Trying again, okay, etc., etc. So, how would you figure it out? Well, we're trying to solve for time. So obviously from math class, you remember, if I wanted to say calculate the time, I would need to know all these other variables. So let's see, for this equation number 1, I'm trying to solve for time. Do I know the final velocity? Yeah, I do, it's 5. Do I know the initial? Yeah, it's 0. Do I know the acceleration? Ooh, uh-oh. I don't know the acceleration. So I cannot use number 1 right away to calculate time because I have 2 unknowns. I don't know the acceleration and I don't know time. This is why I actually like this problem, because for these 3 equations, you need 2 different steps. This is a 2-step physics problem. None of these equations listed here will allow you to calculate the time because there are multiple unknowns. So the first thing you actually have to do is find the acceleration. Now, this isn't going to be all the problem, so don't worry. Some of them are going to be easier, just 1 step, but sometimes there are going to be these 2-step physics problems where after you solve for one thing, then you can solve for what you're looking for, in this case, time. There is one equation that I can use that will allow me to first calculate the acceleration. It's equation number 3. So let's try it. I can solve for acceleration because I know the final velocity, that's 5, the initial velocity is 0, and the change in position, the displacement, is 4. Let's do it. V squared equals V naught squared plus 2a delta x. You don't always need those parentheses for delta x, as long as you're aware that delta x, that's one number, right? It's not 2 things being multiplied. So v is 5, so that's 5 squared equals 0 squared plus 2 times a times 4. Okay, 5 squared is, of course, 25. That's 0. I'm just going to drop it. 2 times 4, that's 8. That's 8a. So now I could divide both sides by 8. I get a is equal to, I wrote it down on my piece of paper right over here, 3.125. 3.125. That's meters per second squared. So now I know what the acceleration is equal to. Now, is there an equation that I can use to calculate the time, what it's ultimately asking? Yes, equation number 1. Because I know that final and initial velocity, now I know the acceleration, and I can calculate time. Let's do it. V equals V naught plus AT. Final velocity was 5. Initial was 0. Now I know the acceleration. Multiply it by t. So now I'm just going to divide both sides by that 3.125. I calculate a time of 1.6 seconds. Again, I just round after 1 or 2 decimals. Don't have to use sig figs. Don't have to use that 3 decimal place rule. That's my final answer. I like to box my final answer. 1.6 seconds. Okay? That's it. Hopefully you got 1.6 on your own, or if not, maybe you understand why now. Thanks a lot for watching this video. That's it for constant acceleration.